Section 7.5 is on sequences again, but now I'll show you nonlinear sequences. I'm going to give you some examples of sequences that are not linear, such as n squared, n cubed, or even when n is the exponent itself. Remember yesterday we looked at linear sequences. In a linear sequence, the difference between the terms is the same each step, right? Here it was a difference of 4, adding 4 with each step. Here it was subtracting 7 each step, because the difference between terms is the same throughout the sequence, here as well as here. These sequences were linear. So now I'm going to show you some sequences that are not linear. The square numbers, 1, 4, 9, 16, 25, 36, etc. Right? This is term 1, term 2, term 3, term 4, term 5, term 6. Now, the difference here is plus 3. The difference here is not plus 3, which means it's not linear, right? The difference here is 5. The difference here is 7. The difference here is 9. Plus 9. The difference here is 11. Okay. The cool thing about this one, these are the squared numbers, right? So the position of the term n squared, right? Forgot to write that down. Right? Fifth term is 5 squared is 25, right? So this sequence is described by this algebraic expression. And the cool thing is here that the difference between the terms are not the same, but there is a cool pattern within the difference between the terms, right? We added 3, then 5, then 7, then 9, then 11. And I think you noticed the pattern already. It's a difference of 2, 2, 2, 2. So the difference between the differences are the same. That's cool, right? N squared. Let's see if we can find a similarly cool pattern in the cube numbers. Any term in the sequence of cube numbers would be the number of the term cubed, right? So the first term would be 1 cubed, the second term would be 2 cubed, the third term would be 3 cubed, etc. Let's write the numbers. 1 cubed is 1, 2 cubed, 2 times 2 times 2 is 8, 3 cubed, 3 times 3 times 3 is 27, 4 cubed, 4 times 4 times 4 is 64. The fifth term, 5 times 5 times 5, 5 cubed is 125. The sixth term, 6 times 6 times 6 is 216. I'm doing this all in my head. Right. Let's write this above it. Second term, third term, fourth, fifth, and sixth. All right. Let's see. Here, the jump is 7. I'm leaving out the plus. I'm just going to write a negative when it's negative, if that's all right. This jump is 19. This jump is 737. This jump, 61. This jump is, I don't know, 91? Yes. All right, so these differences are all different. So it's not linear. We knew that was going to happen. Let's look at the differences between the differences. 12, 18, goodness, 40, 24, and 30. Wow, these are still all different, right? But if you look carefully and you are good with your numbers, you notice that the differences between the differences are all going to be the same. See? Here we add 6 in each step. So, whereas n squared became semi like linear in the second layer, right? The differences between the differences were the same. Here with n cubed, the differences between the differences were the same. So there's a third layer here. Cool, because there's a 3 there and there's a 2 there. So we like that pattern, right? It's good to recognize this pattern, to know that this means n cubed, and to know that this kind of pattern means n squared. Except I promised you I would show you n squared, n cubed, but also 2 to the power of n. So let's do 2 to the power of n. So that's a sequence where any term in the sequence is going to equal 2 to the power of the number of the term. That should be term 1, term 2, term 3, term 4, term 5. T1 is going to be 2 to the power of 1, which is 2. T2 is going to be 2 to the power of 2. 2 squared is 4. 2 to the power of 3. 2 times 2 is 4 times 2 is 8. The fourth term is going to be 2 to the power of 4, which is 16. Term 5 is going to be 2 to the power of 5, which is 32. See, we actually multiply this term by 2, and then this by 2, by 2, by 2. Okay, let's look at the differences between the terms. Here we added 2, here we add 4, here we added 8, here we added 16. Ooh, what happens here? Is there anything cool? From 2 to 4, it's 2. From 4 to 8, it's 4. 8 to 16 is 8. Oh my goodness. This is just going to keep going. See? The differences between the differences are the same as the original differences, right? So this is going to keep, if this list was longer, it's just going to keep on going. 2, 4, 8, 16, 2, 4, 8, 16, 32, 2, 4, 8, 16, 32. So we're never going to get to a level where the differences are going to be the same. And that's what 2 to the power of n looks like. Okay, we could actually say, if we rewrote this, T1, T2, T3, T4, T5, 2, 4, 8, 16, 32. The thing that we could say is the returning pattern is that we're multiplying by 2. Right? And the number of times we've multiplied by 2 is going to be this exponent, which is the number of terms, right? So the fifth term, we've multiplied 2 by itself 1, 2, 3, 4, 5 times. All right, cool.